Hello, everyone. I hope everybody's well. Let's go ahead and take a look at Rolle's theorem, and then we'll do this one example that we see on the screen. Rolle's theorem says the following statement. One, f must be continuous on the closed interval AB. F must be differentiable on the open interval AB. And the third condition is that the endpoints are equal. So f of A and f of B must be equal to each other. So when you evaluate the function at the end point of the interval, they must be equal. Then we can make the following conclusion that there exists a number C in this interval such that the derivative at that C must be zero, meaning we have a horizontal tangent at that number C. Now, before we dive into the example, let me show you a picture. That way it can help you remember the statements easily. So suppose you have f, there's a nice continuous function, differentiable. So we'll draw a nice smooth function like that. Here are the endpoints. So I'm assuming they're the same. So let's call this f of A. Let's call this f of B. Now, if that's the function, then we know at some point, so if this is the interval from A to B, so suppose this is A, this is B, f of A is equal to f of B. That means at some point within this interval, the derivative of this function must be zero. So let's call that is where this happens, and the derivative here is equal to zero. So the derivative of the function at C must be zero. So that is the big picture. I try to simplify it that way. It's easier for you to remember. Let's go ahead and verify that for this function within that interval. You don't have to necessarily draw a picture. So first thing we're going to do is verify that it is continuous. So one, f is continuous on the interval -1 to 3. Is that true? Yes, because f is 3x squared minus 6x plus 4. In fact, it's continuous over the entire real line. So f is continuous on this interval since we can justify f is a polynomial of degree 2. All right, the second thing we're going to write down is, now, does the derivative exist throughout the open interval -1 to 3? That's also true. So f is also differentiable over the interval from -1 to 3. Since it's a polynomial, the derivative exists everywhere. So you can justify that as well. Now, the third condition we need to check is if the function values are equal at the endpoint. So is f of -1 equals f of 3? So we're going to check that. So let's check that. Evaluate f of -1. Plug in -1 into f. You'll have 3 times -1 squared minus 6 times -1 plus 4. That's going to give you 3 times -1 is -1 squared, that's 1, so that's 3. 6 times -1, -6 times that's +6 plus 4. This is going to give you 6 plus 4, that's a 10, plus 3, that's 13. Now let's find f of 3. So we'll do 3 times 3 squared minus 6 times 3 plus 4. Let's evaluate that. So 3 squared, that's 9, times 3, that's 27, minus 6 times 3, that's 18, plus 4, that will also be 13. All right, so we see these are equal. All right, now we can verify our third statement, the conclusion of Rolle's theorem, that the derivative, so because the first 3 conditions true, now we can find the derivative of this function, evaluate it at some c, we can set it equal to 0, and then we can find that c. So I'm going to take the derivative of the function. So this is my function. Using the power rule, we differentiate. So now again, to make this easier, I will just copy this over for us on the bottom. So here is my function f. And now I'm going to take its derivative term by term. So f prime of x is equal to, using the power rule, this is 3 times 2, that's 6x, minus the derivative of 6x is 6. Now I replace x with c, so I f prime at c, this is going to be 6 times c minus 6, and then we want it to be 0. We find c, so you have 6c is equal to 6, adding 6 to both sides, and then c must be equal to 6 over 6, that's 1. Now, is that within the interval? it should be, it is, right? Our interval is -1 to 3. So that is the number C, satisfies Rolle's theorem. I hope this makes sense. Take care, everyone.